CSE 215. Questions. I know there were at least some questions on the homework. This would be a great opportunity to go over those.
My question was so I was working my way through like the proofs, the homework, and
Mhm.
I mean I was doing some stuff wrong, but then I realized, is it possible if I'm given a couple premises, is it possible for me to get to a conclusive statement without using like all the premises? So let's say we're given like three premises and I'm working through a proof and then I use two only. Is that something that's possible?
It's certainly possible. Um, it's something I would consider kind of a sneaky trick for someone to do. Because usually if you're given, prove the following, and you're given three premises, normally you would want to use all three of those. If someone wanted to, make it extra challenging, they might give you a problem where one of those premises had nothing to do with anything. That could happen. And, I mean, you can take any proof problem like prove this and this and this imply that, and I could add on a fourth, fifth, and sixth premise that have nothing to do with anything. So it's certainly possible. I don't think that comes up in those problems that were assigned. But if you encounter something like that, yeah, it's definitely a possibility. Did you find that in one of these problems from the homework?
I didn't find it, but then I think I was working on problem 4C, and then I was trying to relate C and D, that premise with the
Hmm.
whole proof, and I think I was doing something wrong until I realized, oh, so yeah, that's how the question came by, and I think
Okay.
that also answers my other question of where we are given like a couple promises that are not related to the proof. So yeah.
Hmm. Yeah, so it can happen. It usually doesn't. I usually try not to, give you these would be called red herrings. I try not to give you, these extra things that are just there to make you doubt yourself or to make it more confusing. But yeah, it's possible. Um, Question 4C is an interesting one. It's interesting partially because there's this D right here. And D doesn't appear anywhere else in any of the premises or in the conclusion. And that's, I mean, it could be just there to, make things more interesting. Um, but it tells us there's something special going on here, right? C and D. Um, and so the idea here, you're told that C and D is true. We don't know what D is. It doesn't affect anything else. So this must be significant, right? The C part of this. Well, if C and D are true, what do we know about C?
Mhm. So I can
So C and D are true. What do we know about C? C must be true, exactly. And that kind of gets you off and running. If C is true and A implies that C is false, that tells us A has got to be false, right? That's either indirect reasoning or we can take the contrapositive of this and see C implies not A. And if A is false and A or B is true, B's got to be true. So I think that's kind of an interesting one. Let's see. Question in chat. Indirect proof of problem B. So let's take a look at that. Um, Let me write this down and then I'll bring up the camera. So P implies not Q, not R implies. Q, P, and we want to get to R. All right, so here's what we're trying to prove, right? We've got three premises. We're working for one conclusion. So P implies not Q, not R implies Q, P, and we're trying to conclude R. So an indirect proof, start off by negating the conclusion. So let's say proof. So proposition one, I'm going to say not R, and that's the negation of the conclusion. And I'm going to try to get a contradiction out of that. Well, I've got not R and I've got something which says not R implies Q. So let's put those together. So let me do proposition two. Not R implies Q. And that's a hypothesis or a premise. Proposition three, I'll combine those and that will give me Q. And that's direct reasoning or detachment. And at this point, if I look at my premises, I see that I have P and I have P implies not Q. I can put those together and that'll give me not Q. So let's go ahead and say P. That's a hypothesis. P implies not Q. That's a hypothesis. And 4 and 5 together give me not Q. That's more direct reasoning. 4 and 5. And there's my contradiction between 3 and 6. So that's one path to a contradiction. There's other ones I could have done. Once I have Q, I could bring in P implies not Q, use indirect reasoning to get not P, and then I could bring in my hypothesis P, and P and not P would contradict. There's a number of contradictions I can derive once I've started with not R. Any contradiction will suffice. In this case, Q and not Q works. So I would say, therefore, R, and that's what we were trying to show. So that would be one indirect proof for part B. Does that help? Cool. Welcome. Nice. Other questions?
Professor, can you go through the 3.4 problem two in indirection proof?
3.4, number 2. The common fallacy.
Yes.
To show the common fallacy is not a law of logic. Okay, that's a good one. So they tell us what the fallacy is. So um, show P implies Q and not P implies not Q is not a law of logic. So I think the way I would approach this would be to try a truth table and make a truth table for P and Q, find this, find this, find their conjunction, fill in not Q, and show that this does not always imply that. So P, Q, and I don't know if this will work or not. I haven't actually done this. Let me use zeros and ones for false and true. So P implies Q is always true except hypothesis true, conclusion false. So it's ones everywhere except that. Negation of P is just 1, 1, 0, 0, negation of that first column. And then we take the conjunction of these two. So 1 and 1, 1 and 1, 0 and 0, 1 and 0. And then negation of Q is just the negation of the second column, 1, 0, 1, 0. And it looks like right here we've got a problem because this is certainly true in this case, right? But not Q is false. So if we claim that this always implies that, it means anytime this is 1, that has got to be 1. Well, here's a case where this is 1, but that is a 0. So this cannot always imply that. So this is not a law of logic.
So I just need to prove it by truth table, and don't need to prove it in indirection proof.
Any way that you can prove it will work here. It doesn't require a direct or an indirect proof or a proof at all. And so yeah, truth table is a pretty good mechanical way to go about showing these kinds of things. I'm not sure how I would do this with like a direct proof or an indirect proof. Because we're trying to show that something is not a law of logic. Um, I guess we could assume this was true and try to find a contradiction. Um, but I don't know an easy way to do that. Certainly not a way that's easier than just finding specific values for P and Q. In this case, if P is false and Q is true, that gets us the contradiction. Um, what's interesting also is to kind of think about what this means, right? Why is this not a law of logic? Well, this says if P, then Q, and then we deny the hypothesis. We say not P, and we try to conclude not Q, right? So if I win the lottery, then I will have dinner tonight. I don't win the lottery, so I'm not going to have dinner tonight. Well, that's not true. I'm going to have dinner regardless. So where does this contradiction pop up? Well, when this thing is true, right, and the hypothesis is false, but the conclusion is true, right? I did not win the lottery, but I'm still having dinner, right? And that's this case here. The hypothesis is false, but the conclusion is true. So that kind of thinking about it intuitively also leads me to look at this case. And if I write this out, yeah, this is true, that's false. So it's not a law of logic.
Yes, does make sense. Thank you.
Okay, cool. I find the whole connection between truth tables and statements like this sometimes kind of nebulous, kind of confusing. I can work through the steps and I can, nod my head and say, yeah, okay, clearly that does not imply that. It's not a law of logic. But making intuitive sense out of that, sometimes that's challenging to me. Um, and so trying to come back and think of, different examples and what these variables mean in those examples, sometimes that helps. Um, again, the kind of nice thing about propositional logic is we don't necessarily need that understanding. Um, The unfortunate thing about propositional logic is sometimes we don't get that intuitive understanding, right? So it works both ways. All right, good. Other questions? All right, well, let me talk about the next homework assignment, which is due a week from today. Let me bring up Canvas. So homework 4. And homework 4 is all here in the Canvas shell. It's not coming out of the textbook. So I've written some problems for you to work on. So this first question is different from the others. In this first question, I say define propositions P and Q and use them to give two real-world examples of the fallacies we've discussed, denying the hypothesis, affirming the conclusion. So I'm not asking you to do a truth table. I'm not asking you to do a formal proof. I'm asking you to do something like this. And don't do this one because I'm giving it to you right now, but you've heard me do this one before. Let P be the proposition, I win the lottery. Let Q be the proposition, I eat dinner tonight. And then say, if P, then Q, not P, therefore not Q. That's the fallacy of denying the hypothesis. Well, that fallacy claims that if I don't win the lottery, I'm not going to eat dinner. But in fact, I'm going to eat dinner whether I win the lottery or not. So that is clearly a fallacy, right? It's not a law of logic. Okay, that's an example using particular propositions P and Q that illustrates that that fallacy is in fact a fallacy. And then I could come up with another example or maybe the same propositions for the fallacy of affirming the conclusion. In this case, if I win the lottery, then I will eat dinner tonight. I eat dinner tonight, therefore I won the lottery. And that's clearly a fallacy also because, as I've told you, I'm going to have dinner tonight regardless. And so you can't conclude that I won the lottery. So I want you to come up with your own examples for question 1. Think about, propositions P and Q where P implies Q, but not P does not imply not Q, right? Try to come up with your own examples that illustrate these fallacies and then just write them out, right? Let P be the proposition, let Q be the proposition. Here's what P implies Q says, here's what not P says. But in fact, not Q does not follow from this. And just pick some example from your life, real or imagined, but something that somebody reading this would be able to see, okay, yeah, so that's clearly a fallacy. All right, so that's question 1. It's different from the other questions. These other questions, you're writing formal proofs. So you're going to state what you're trying to prove, write the word proof, start going through a bunch of steps, direct or indirect, your choice. So question 2, if n is even, 6n plus 4 is even. Question 3, if n is even, n squared plus n is even. Questions 4 and 5, we've done some versions of these. You get to do them yourself now. If n squared is even, n is even, and if n squared is odd, n is odd. And then question 6, this is about divisibility. If a divides x and a divides y, then a divides 5x minus 3y. And this will follow from the definition of this proposition. So you need to go back and you need to review what this proposition a divides x means. And there's a definition we gave of it, right? There exists an integer k such that x equals a times k. or there exists an integer j such that y equals a times j, and use those definitions, try to prove that there exists some integer L such that 5x minus 3y equals L times A. So these 5 questions are very similar to each other in how your answers are going to look. They're going to have the same set of steps. The details will be different, but not very different. What I've put up here are some of the important things to keep in mind while you're doing formal proofs. Whether it's these questions, other homework questions, proofs on exams, and so on. So just as a reminder, when you do a proof, start off by stating what you're trying to prove, right? In other words, write down the problem. Prove if n is even, then 6n plus 4 is even. Write that out in words at the top of this question. And then write the word proof. And after that, everything you write has to be a proposition, a declarative statement. So you can't write x squared. You can't write 6n plus 4. But you can write x squared is bigger than x, or 6n plus 4 is such and such, right? So they have to be propositions. Every proposition is true because it follows from the previous steps and laws of logic, or because it's a hypothesis, if you're doing a direct proof. If you're doing an indirect proof, you get to write one thing that's an assumption, which is the negation of the conclusion. Every proposition has a number to the left of it and a reason why it's true to the right. And your final proposition should be the thing you're trying to prove. And remember, if you're doing a proof by contradiction, your final statement is not contradiction. Your final contradiction is whatever you said in the beginning that you were trying to prove. So write that final proposition and then put the words QED. So we've done this a bunch of times in class. You should have lots of examples of it. If you want more examples, ask now or come by office or something, and I'm happy to go through other examples. And again, this is all rehash of what the book is doing. Different language, right? Premise instead of hypothesis, square box instead of QED, and so on. All right, so questions about that? All right. So let's keep going with number theory. So we've talked a fair amount last time about prime numbers, numbers that have no factors other than itself and one. But most numbers are not prime. Primes are relatively rare, especially if you look out at very big numbers. Most numbers are not prime, meaning most numbers have factors. And one thing that's interesting is finding factors that are common to two numbers. So two numbers, and is there something that divides both of them? Well, we know that one divides both of them. And if both numbers are even, we know that two divides both numbers. But sometimes what we're interested in is the greatest common factor or the largest common factor. Or sometimes the greatest common divisor. So you'll see this written as GCF or maybe GCD. And one place where greatest common factors are useful to us is, in school when we're learning about fractions and we're doing calculations with fractions and we end up with a number like 25 over 15. What do? We try to simplify that. And we could simplify this as 5/3. Well, how do we do that? How do we go from 25/15 to 5/3? Well, in this case, I divided the top and the bottom by 5. But if I had done a calculation and I came up with 250 over 150, and I divided the top and bottom by 5, I'd get 50 over 30. And that's still not in simplest terms. And I could divide by 2 and I get 25 over 15, but that's still not in simplest terms. I have to divide by 5, and now I get 5/3. So what we do, and we usually don't do this explicitly, we're kind of doing it in our heads maybe, but we're finding the largest thing that we can divide both of these by and still get whole numbers. So in this case, we divided by 50. And in this case, we divided by 5. And in this sub-step, we divided by 2. But we could have divided by 10 and gotten all the way over here. So an interesting question is, given two whole numbers, what's the greatest number, the largest number that divides both of them? And it turns out we have an algorithm for doing that. And you definitely want to know this algorithm. It'll pop up in homeworks, but it'll definitely be on at least one test somewhere. So this is called the Euclidean algorithm. So we're back to Euclid. And let me just give you an example of this algorithm. And I could write out a series of steps, but it would be way more confusing than just kind of doing some examples. So let me give you an example. Let's do this 250. Let's find the greatest common divisor of 250 and 150. And we said earlier, it's going to be 50, divides them both. But here's how the algorithm works. Take your larger number and write it as something times your smaller number plus some remainder. So 150 will go into here exactly once, and we'll have 100 left over. Now bring your numbers down and do this again. Write 150 equals something times 100 plus something. Well, 100 goes into here exactly once, and we have 50 left over. Bring your numbers down again and write 100 equals something times 50 plus something. Well, 50 goes into 100 twice, and there's nothing left over. When you get to this step, that's your greatest common divisor. So 50. That's the whole algorithm. So let's do a few more of these. So let's do the greatest common divisor of 735 and 252. So 735 equals something times 252 plus something. So I'm going to be lazy and use a calculator. So 252 If I try to put it in 3 times, I'm going to be above 750. So this is going to go in twice. And let's do 735 minus 2 times 252. I'm going to have 231 left over. Bring these numbers down. 252 equals something times 231 plus something. Well, 231 is only going to go in once. And if I subtract 231, I'm going to have 21 left over. Bring your numbers down again. Let's write 231 equals something times 21 plus something. If I do 31 divided by 21, that goes in exactly 11 times. So 11 times 21 plus 0. Once I get to the 0, this is my greatest common divisor. Math is always magic. So this tells me two things. One, both of these numbers should be divisible by 21. So let's check that. 735 divided by 21 is 35. And 252 divided by 21 is 12. So they're both divisible by 21, but it also means that these should have no common factor. If both of these were divisible by 2, then I could have divided these numbers by 42, right? 2 times 21, and this would not be the greatest common factor. So once you find the GCD, you can kind of double check your answer. Number one, make sure it divides both of these. And then make sure that once you divide each of these by that GCD, what you're left with has nothing in common. Well, how do I know that 35 and 12 don't have a factor in common? I mean, I could try some numbers, but another thing I can do is I can write these as products of primes. 35 is 5 times 7. 12 is 2 times 2 times 3. Now, if there was a 3 up here, or if there was a 2 up here, or if there was a 7 down here, I'd have another common factor. But since none of these primes appear up here and vice versa, I know there's nothing that divides both of these except 1. So that's Euclid's algorithm. And again, this is another algorithm that's very easy to teach a computer. Um, and it's useful for a number of things. All right, questions about that? All right, so give it a try. Go ahead and find the GCD of 525 and 180. And take a few minutes. Send me a direct message if you get an answer. Send me a direct or indirect message if you're stuck or have questions on how to do this. And we'll take about 4 minutes and try that. All right, cool. Got lots of good answers. Um, so yeah, let's just run through the algorithm. So 525, 180 times 3 is going to be close to 600. That's going to be too big. So this will go in twice. That's 360, 460, 520, 525. This will have 165 left over. Bring these down. 180 equals something times 165 plus something. 165 goes in once, 15 left over. Bring these down again. 165 equals something times 15 plus something. So 10 would be 150 plus another is 165. So this just happens to turn out to be 11 of these plus 0. So your GCD is 15. And so if you do 525 divided by 15, that should give you, I believe, 12. And if you do 180 divided by 15, that should give you 35. And no common factors there. And I just came up with these numbers while I was talking a moment ago by taking powers of primes. Oh, I think I got these wrong. Okay, I'll cheat and use a calculator. Yeah, I got these wrong. So 180 is 2 squared times 3 squared times 5, and 525 is 3 times 5 squared times 7. And if you can write these numbers as products of primes, and we know we can do that, you can sort of ferret out what the common divisors are. There's no 7 up here. There's a single 5, and there's a single 3 that's common. So the GCD is going to be 3 times 5. But that requires one, factoring into primes, and then two, kind of looking at it and trying to figure out what's in common. Euclid's algorithm, there's no guesswork. It's very programmatic. Another nice thing about Euclid's algorithm, if you're coding this, and you happen to have your numbers in a different order. So suppose someone said, find the GCD of 180 and 525. You would start off by saying 180 equals something times 525 plus something. Well, 525 goes in 0 times, and you're left with 180. And then when you bring those down, your next step is to write 525 equals something times 180 plus something. Well, that's, the first step that we did when we started with the numbers in this order. So it's kind of self-correcting if you happen to have your numbers switched. The same algorithm works, and that's nice when you're coding this in a computer because you don't have to actually order your numbers. If one or both of these numbers is negative, though, I would throw out the negatives, right? And just work on the absolute value of the numbers. And greatest common divisor, if our numbers are negative, I don't know if that's the most negative or the least negative, but that's usually not an interesting question. It's more just look at the magnitude of these numbers, find the GCD. But those are things you have to worry about if you're actually coding this. All right, so we can find greatest common divisors. And this brings up an interesting question. For example, the GCD of 12 and 35. Right, so 35 equals 2 times 12 plus 11. 12 equals 1 times 11 plus 1. 11 equals 11 times 1 plus 0. So your GCD is 1. Right? There is no common divisor for 12 and 35 other than 1 itself. Now, 12 is not a prime number. It's divisible by 2, 3, 4, and 6. 35 is not a prime number. It's divisible by 5 and 7. But if we have a pair of numbers and their greatest common divisor is 1, we use the term relatively prime. So two numbers, A and B, are called relatively prime if their greatest common divisor is 1. Which is another way of saying if we write a fraction of A over B or B over A, it's in simplest terms. And if we pick two prime numbers, like 23 over 17, those are definitely relatively prime, right? Because there's no factors for 23 except 1. There's no factors for 17 except 1. So anytime you have two different prime numbers, they're automatically relatively prime. But there's numbers that aren't prime that are still relatively prime to each other. All right. Next question, solving congruences. So we know how to solve linear equations. If I tell you 5x equals 15, you can tell me x equals 3, right? We divide both sides by 5. But if we're working with congruences, for example, if I say ax is congruent to b modulo m, and I tell you what a and b are, and I tell you what m is, can you find what x is? And that's kind of a hard question. If you think back to our multiplication tables, remember in some cases, every row and every column had every value between 1 and m minus 1. But in some other cases, there were rows or columns with missing numbers. And in those cases, there may be equations like this that don't have a solution. So do you remember what the difference was? What was the condition for every row and column to have every number between 1 and m minus 1? There was a pretty simple...
It had to be prime.
Had to be prime, right? If m is prime, then this multiplication table is nicely behaved. So what we can say is if m is prime, then we do have a solution for this, as long as b is not 0. Well, I mean, if it's 0, there's a trivial solution. But if M is prime, there's a solution to AX is congruent to B. And in fact, generally it's a unique solution. And the solution is basically, whatever A is, find the column where B is. Right? So we could read that off of a multiplication table. So if you're given A and B, there exists a unique X. Remember that exists. If we put an exclamation mark, that means there exists a unique X such that AX is congruent to B. If M is not prime, there may not be solutions. So you can do a whole study on that. We're not going to dig too deeply into it, but it leads us into the final kind of theoretical part of this, which is something called the Chinese remainder theorem. And we're not going to prove this. I'm not even going to go into the details of how this works. I'm just going to tell you what this theorem says. And it does, date back to ancient China. The Chinese remainder theorem is about solving systems of equations of congruences. So for example, suppose I tell you that x is congruent to 2 modulo 3, and x is also congruent to 3 modulo 5, and x is also congruent to 2 modulo 7. And I ask you, what is x? So x is something that's 2 more than a multiple of 3, 3 more than a multiple of 5, 2 more than a multiple of 7. And it turns out, for example, the number 23 satisfies all 3 of these. It's 2 more than 21, which is a multiple of 3. It's 3 more than 20, which is a multiple of 5. And it's 2 more than 21, which is a multiple of 7. So that's a solution to these 3 equations. It turns out there's an infinite number of solutions. 23 is the smallest one. All I want you to remember for today and maybe Monday about the Chinese remainder theorem is the following. If you look at these moduli, 3, 5, 7, and there could be more than 3 equations, there could be a whole slew of them. But if you look at these moduli, 3, 5, and 7 in this case, if these are all pairwise relatively prime, in other words, 3 and 5 are relatively prime, 5 and 7, 3 and 7, if each pair of these are relatively prime, then there is a solution. I did not go over how I got 23. I pulled it out of thin air. There's an algorithm we can use. I'm not going to go over the details of it. It's a page of calculations, and it doesn't do us any good for what we're going to do. So I just pulled this out to show you that there is a solution, but we didn't have a method for finding that. There is a method. It's called the Chinese remainder theorem. But the fun thing is, once somebody tells you that there's a solution, you can verify it, right? And so that's all we want to do here is verify that is congruent to these things. So the takeaway from the theorem is if these are pairwise relatively prime, there is a solution. And then there's a series of steps you can go through to actually find that solution. Not responsible for that. So certainly when these are prime numbers, we know they're pairwise relatively prime. So there's going to be a solution. All right. That's the Chinese remainder theorem. These are some facts that are going to be useful for what we're going to wrap up this chapter with, either later today or on Monday. Let me give you one more fact. This is called Bézout's theorem. It's an accent like that. So, given two numbers a comma b, there exist integers x comma y such that a times x plus b times y equals the GCD of a comma b. That's a cool little theorem. If you've done or are doing linear algebra, this part over here is just, we would use the phrase a linear combination of a and b, meaning a times some integer plus b times some integer. Bézout's theorem says given a and b, there's a linear combination that's equal to its GCD. In particular, if a and b are relatively prime, the GCD is 1, there's some linear combination of a and b that's equal to 1. Meaning, among other things, if I pick any two prime numbers, I can find a linear combination of them that adds up to 1. For example, if I take 3 and 7, I could do 1 times 7 plus negative 2 times 3, and that gets me to 1. If I do 5 and 7, I could do 3 times 5 plus negative 2 times 7, and that gets me to 1. So Bézout's theorem says I can always do this. I can always find whole numbers x and y such that ax plus by is their GCD. We're not going to prove that. We're not really going to use it except for one thing, which will be related to cryptography. But we'll come up to that later on. All right, one more theorem, and then we'll take a break and we'll start talking about applications after a break. But we got to talk about Fermat's little theorem. Which has the same abbreviation as Fermat's last theorem, but this is proven. This was proven by Fermat, presumably. So if P is prime, and P does not divide A, so P does not divide A. In other words, A is not a multiple of P. Then A to the P minus 1 is congruent to 1. modulo P. And this is actually not too hard to prove. If you do a course in abstract algebra, it's one of the first proofs you might encounter. If P is prime and A is not a multiple of P, then A to the P minus 1 is one more than a multiple of P. So for example, 17 is prime. So I'm guaranteed that 8 to the 16th is congruent to 1 modulo 17. And 8's not a magic number. Any number that's not a multiple of 17 raised to the 16th is congruent to 1 mod 17. So that's what Fermat's little theorem tells us. So let's double check that. So there's 8 to the 16th. There's 8 to the 16th minus 1. There's 8 to the 16th minus 1 divided by 17. It's a whole number. So 8 to the 16th is one more than a multiple of 17. That's what Fermat's little theorem is telling us. Which brings us to the question, so what? Why is that an interesting or a useful fact? Well, it's interesting for doing calculations on large numbers. So we looked at modular exponentiation on Monday. My last sheet of sloppy scratch paper. We can use this fact to do large calculations very efficiently. So suppose someone says find 8 to the, I don't know, 16,002 modulo 17. So 8 to the 16,002 is a big number. It's that. We don't want to do calculations with that number. So what we can do is we can use Fermat's little theorem to cut through most of the calculations. So we could say as follows: by Fermat's, sorry, little theorem, not last theorem, by Fermat's little theorem, 8 to the 16th is congruent to 1 modulo 17. Well, I can jump from there all the way up to 8 to the 16,000, because 8 to the 16,000 is 8 to the 16 times 1,000, which is 8 to the 16th raised to the 1,000. So this is another law of exponents. And since Fermat's little theorem tells me 8 to the 16th is congruent to 1, this is congruent to 1 to the 1,000th, which is just 1. So I just cut through 16,000 multiplications in 3 lines of writing. So 8 to the 16,000 is congruent to 1. 8 to the 16,001st is congruent to 8. 1 times 8. 8 to the 16,002 is congruent to 8 times 8, which is 64. And 17 times 3 is 51. So this is congruent to 13. And there you go, 16,002 multiplications reduced to a few lines of calculation. You'll get homework questions later to practice on these. All right, so let's take a break. Let's come back in about 5.5 minutes, and let's start talking about some of the applications of these fairly abstract ideas. All right. So why is any of this stuff useful? Other than, parlor tricks for dividing numbers by 11 or something like that. Um, we use this stuff in a lot of different places in computer science. Um, and I want to go over a few examples. The simplest one being what we call parity. So before we had Wi-Fi, before we had Ethernet, um, computers were connected using telephone lines. And when people first started doing this, you were not allowed to plug anything into a phone jack unless you were using equipment that you bought or rented from Bell Labs, right? They owned the copper in the walls of your building, and you were legally prohibited from using that copper with your own equipment. So you couldn't plug a modem into the wall. But after a number of court cases, it was decided you could send sounds over a phone and you could use your own equipment to generate those sounds. And the phone company prohibited you from doing that for a long time, which meant things like modems and fax machines were illegal. But finally, after multiple court cases, the courts ruled in favor of the public and said, okay, as long as you're not actually electrically interacting with the copper directly, you can send whatever you want over the phone. And so people started selling and using modems. And modems were devices that would make tones that would go through the mouthpiece of a phone. And then a phone connected on the other end, the speaker would go into a microphone and you could code information in these tones. So if you listen to old techno music and you hear all those buzzing sounds, that's modem noise, right? Um, and this allowed computers to be connected together, and early networks were built um, using this technology. One of the problems was it was error prone because, a high tone means a zero and a low tone means a one. But they're just sounds. And if, someone turns on the TV really loud and there's a sound that's similar to one of these tones, the computer receiving that audio signal might get confused and think there was a different bit from what was actually sent. So a typical problem was you might want to send a piece of binary information like this. And because there might be noise on the line, or maybe, the line drops out, or maybe someone picks up the extension and there's a clicking sound and so on. Maybe this bit got flipped from a zero to a one. And, if this is data, your data is corrupt. If this was the code for an executable program, your program is going to crash when you try to run it because it's got the wrong opcode here, right? All kinds of problems. So how do you detect this? And an easy way to do this is to use what's called a parity bit. And so the idea of a parity bit, for example, odd parity. So you append, let's say all your data is 8 bits, append a ninth bit. So we'll add one extra bit here, which we call the parity bit, such that the total number of ones is odd. So for example, if I wanted to send this number 0110101, well, that number, I've got a total of 4 ones. That's an even number. I would set my parity bit to a 1. And I'm sending 8 bits of information, but I would actually send 9 bits. I would add this parity bit to the end. On the receiving side, when I get a number, I add up those 9 bits, 1, 2, 3, 4, 5, 6, and I look at that modulo 2, and I get a 0, I know I've got an error, right? Because if the number of bits that are 1 is odd, When I add those up, I'm going to get an odd number, and odd number modulo 2 is going to be 1. So by adding up those 9 bits, reducing it modulo 2, I can tell if there was an error in the transmission. And if, in fact, the error is in the parity bit itself, same thing, right? If this parity bit's supposed to be 1, but it comes out as a 0, I would add up my 1 bits. I would get 4 modulo 2 is equal to 0. I'd still say there was an error. Now, I don't know where the error is, but I know something's wrong, and I would send a message back saying, hey, send that last byte again, and would retransmit, and hopefully would actually come through like this, and I'd add up the ones, 1, 2, 3, 4, 5. Modulo 2 is 1. Okay, that's good. So what's the big weakness with this approach? What's the biggest problem with it? Yeah, if I get 2 bits flipped, I'm never going to know. So let's say this 1 also got changed to a 0. 1, 2, 3, 4, 5 bits are 1. Hey, everything looks great. So it doesn't work well if you have 2 bits flipped, but if you got 1 bit flipped, guaranteed to notice. So there are more sophisticated versions of this. This is about the simplest way to do this. But there's things like ECC, error checking and correcting codes. So when you buy memory for a computer, it used to be you could get less expensive memory or more expensive memory. And the more expensive memory had what they called ECC. And ECC is a multi-bit version of parity. And the way it's set up is maybe you have a block of 32 bits, and then you have, say, 3 extra bits. And if a bit gets flipped, it not only tells you that it got flipped, but it can tell you which bit got flipped so you can correct it. And if 2 bits get flipped, in some schemes, you can detect that and you can still correct it. And if 3 bits get flipped, you can detect that there's an error, but you can't necessarily correct it. And depending on how many ECC bits you used, you can do a better and better job of detecting multiple errors and in some cases correcting them. And ECC is very common in memory and in digital circuits in general, because transistors have gotten smaller over time. And as they've gotten smaller, voltage levels have dropped. So in your engineering CSE250 class, we work with circuits where we have 0 volts for a logic 1 and 5 volts, 0 volts for a logic 0, 5 volts for a logic 1. And really, if you're at like 3.5 volts to 5, that's a good logic 1. And if you're anywhere from, say, 2 volts to a 0, that's a good logic 0. And we've got this 1.5 volt gap in the middle. And as long as we stay out of that range, there's no ambiguity. So you're running your signal and you want to generate a logic 0 and you're generating 0.7 volts and someone turns on a hair dryer, maybe that jumps up to 1.1 volts, but it's still a logic 0. Or maybe someone turns on something that draws a lot of current off of your power line and your 5-volt signal drops to 4 volts. It's still a logic 1. But with modern systems, we may see something like 0 volts is a logic 0 and 0.7 volts is a logic 1. And that's it. We've got less than 3/4 of a volt between a 0 and a 1. So if we get a 1 volt drop in our voltage level, zeros and ones change into each other. So as transistors have gotten smaller and voltage levels have gotten lower, right, which is how we make things faster, this noise margin has gotten tighter. So yeah, we still use similar solutions to this, error checking and correcting codes, to try to mitigate these effects. Also, if you're putting systems into space, it's a higher radiation environment. And high energy particles hit your memory and bits will flip, right? And there's ways that you can try to shield your systems from those high energy particles, but that costs money, it costs weight, it adds complexity, right? So a software solution, um, like an error checking code, is usually a better approach. So that's all stuff that like people with like, lots of letters after their name figure out. And it gets into areas of information theory, and things like that. Questions of entropy, and so on. Another area where this stuff kicks in, we're going to do this in 222 starting next week, has to do with hashing. And if you've looked ahead on the videos or done this on your own, you know something about hashing. But the basic idea is to take a large collection of things and reduce it to a small collection of things. For example, you want to store information about songs so that if you hear the beginning of a song, you can tell what song it is, right? So songs are stored in, let's just say, a WAV file. So, you know, several million bits of information to store a few minutes of music. And imagine you have a database with 100,000 songs and you've got 15 million bits for each song. It's a lot of information. And now somebody has the bits corresponding to the first 5 seconds of a song, and you want to look through that database and try to find what song it is, right? That's a really hard problem. So what we do is we take a piece of each song and we run it through a mathematical function and we change it into a smaller number. So instead of being millions of bits, maybe it's 512 bits. And now we have a database with these small numbers. And when we hear a piece of a song, we run that through the same algorithm, get a nice small number, and we try to match that in our database. That's the idea of hashing. And hashing is usually some combination of operations using some of the things that we've been doing over the past week or so. For example, simple example, if I wanted to hash a string, I could make a summation from 0 to, whatever the index of the last character is, and I could take the ASCII code of each character, and I could add all of those up, and then I could reduce it modulo 511. And this would give me a number between 0 and 510 corresponding to this string. Now, my string might have 100 characters in it. It might have 10,000 characters. It might be an entire letter or an essay, but I reduce it into this relatively small number. So now if I have all of these documents stored somewhere, I can also store their hash value, right? The value I get from this function. And if I want to know, is this particular incoming document in my collection? Well, I take that incoming document, I do this calculation, I get a number, I just search for that number. If I don't find it, that document's not in my collection. If I do find it, that might be the document in question. So now I compare the document I'm looking for to the one I have saved and see if it's actually the same. So we can use this for searching. And homework 3 in 222, where we're going to build a dictionary and search for words, we're going to use this idea of hashing. But we can also use this for verification. And one way this pops up is what's called an MD5 hash. And if you've downloaded stuff from the web, you've probably encountered these MD5 codes. You go to a website, you're downloading a piece of software, a game, a plugin, whatever, and the page will show you a big long number, and it says this is the MD5 hash. And the idea is there's some function that you can take what you download and run it through that function, and you get a big long number. And you compare that to the number that you've been told you should get, and it helps you verify, did I download the correct thing? Or did somebody hijack the download page and feed me malicious code? Or did somebody somehow break into that system and inject malicious code into this thing that I'm downloading? So a good hash function will not only take this big long thing like a program and change it into a short number with maybe 4,000 bits to it, but it also has the property that it's really hard to deliberately generate a particular output value. So this hash function, really easy, right? If I want to increase my my hash value by 1, all I have to do is change the letter F to a letter G somewhere. Just bump up the ASCII value by 1. But a good hash function like MD5, it's almost impossible to do that. If I change one piece of my file, if I change a single bit, I'll get a completely different value out on the other side. So if I take a piece of code that you're going to download and I add some malicious code inside to, capture keystrokes or something, and then I try to add some extra stuff to undo the change to my hash code, it's almost impossible to do. That's what constitutes a good hash value for this. So that's why MD5 is considered a reasonable way to ensure integrity of a downloaded file. So we'll be going through this next week in 222 and getting into specific examples, and we'll be sticking with fairly simple hash functions closer to this, but also works for things like MD5 codes and such. All right, another place this pops up is things like universal pricing codes or ISBN numbers, ISBNs. So these are these multi-digit codes that you see. UPCs are 11-digit codes that you find on just about any product that you pick up in a store, and they usually have barcodes associated with them. And ISBNs, if you pick up any published book, somewhere near the beginning, there's a barcode and there's a numeric code, usually 10 digits, but there's different versions of these, 10 digits or characters. Those are unique identifiers to help you identify a particular product or a particular version of a book, and so on and so forth. And just looking at UPCs, so UPC is it's a category, single digit. Is this food? Is it electronics? That kind of stuff. And then there's 5 digits for the manufacturer. And then there's 5 digits for the product ID. So it's an 11-digit code. Well, when UPCs first appeared, the idea was that when you were working in a checkout line and somebody had an item, instead of remembering, This is a number 2 pencil made by Eberhard Faber, and it costs 79 cents, right? You could type in this universal pricing code, and the computer would pull up the price for you. And so you didn't have to know all of these prices, and you didn't have to keep up with the price changes. You would just punch in the code, right? Today we use a laser scanner, but when this first came out, we didn't have laser scanners. So you would just type in this code. Well, one of the challenges is typing in an 11-digit numeric code is error prone, right? You might type in the number incorrectly, and the person thinks they're buying a pencil and you charge them for a color TV, or the other way around. One of the most common typing mistakes is transposition. You're typing a bunch of numbers, and two numbers next to each other get typed in the wrong order. So here's how UPC works. You take, so let's think of this as X1, X2 through X6, X7 through 11. You're not responsible for this. I just want you to see this and try to understand the higher level concept. I'm not going to ask you to give me the UPC algorithm or something like that. So number your 11 digits, X1 through X11, and do the following calculation. 3 times X1 plus X2 plus 3X3 plus X4 all the way up to 3X11. And calculate this modulo 12. And take the result and add one more digit to the end, which we call a check digit. Actually, sorry, do this modulo 10. And if not equal to 0, subtract from 10. So we do this and we get a number between 0 and 9. If you get a 0, leave it as a 0. Otherwise, whatever you get subtracted from 10, that becomes your check digit. So now the person actually types in 12 digits when they're entering your product. And you can do this calculation on the first 11, reduce it modulo 10, subtract from 10 if it's non-zero, and then compare that to the check digit. So it's like another version of parity. The cool thing is it's guaranteed to pick up 100% of all single digit errors. If I get one digit wrong, it will notice. And it'll pick up 90% of the transpositions. And it's because, consecutive digits are multiplied by different amounts. So if I swap X3 and X4, 9 out of 10 times, I'm going to get a different check digit. So it doesn't correct, but it will detect these errors. And then, the register would make a beeping noise, and you type the code in again, type it in correctly, and continue. All right. So lots of applications like that. Last one I want to talk about is cryptography. And cryptography, crypto systems, you can do a whole course on that. There's a lot that goes into this. And so I'm not going to go over a lot of detail, but I want to talk about a little bit of the basic idea of cryptography and crypto systems. Give you a few examples of some simple approaches to this. And then I want to talk about what crypto looks like today and what it is that makes things like internet commerce possible. And then if there's time, this will probably be on Monday, I'll do the very briefest overview of how some of this stuff we've been doing modular arithmetic, prime numbers, Fermat's little theorem, Chinese remainder theorem, Bezout's theorem, how all of this stuff comes together to create a modern crypto system that lets us do things like put a credit card number into the web and be fairly secure that that number is not going to be compromised. Let's talk about cryptography in general first. So what's the basic goal of a crypto system? It's about information hiding, right? You have some piece of information that, let's say you want to share this with somebody else, but you don't want other people to know about it. So, you go over and you whisper something to your friend. And if you're a good whisperer, nobody else can hear. So it's a secret. Um, but what happens if your friend is in another city and you want to give them a message that you don't want anybody else to know about? So you can write the message on a piece of paper and put it in an envelope and put a wax seal on it and stick it in the mail, right? Well, once it's in the mailbox, lots of people have access to it. And, people can break into mailboxes. My mailbox gets broken into sometimes, and people steal the mail, right? Um, you could give it to somebody to hand deliver, but that person could be intercepted. You could give it to a very strong person on a very large horse, and they might run into stronger people on larger horses who intercept them and steal the message. So one of the notions of modern communication systems, there really is no such thing as physical security. You cannot assume that any message that you put out there is uninterceptable. So we have to assume, stuff can be physically intercepted and looked at by other people. This is, even more true as soon as you start using Wi-Fi. Anything you send on Wi-Fi is out there for the entire universe. It's still traveling out of our solar system, out of our galaxy. It's permeating through all of space. It does not go away. And anybody with a receiver can pick that up, right? And receivers cost you a few bucks. And if you've got a Wi-Fi router and you type something and hit enter and it goes to another machine through your wireless connection, whatever is coming out of your router, assume that everybody in the universe has access to that, right? There's no way to secure that. So if everybody can grab this piece of paper and read what's on it, your only hope for security is to somehow make the message unusable to anybody except the person that you want to have use it. So this is the idea of encryption. So we want to encrypt, which is to change plain text into what we call ciphertext or encrypted text. So I'm going to take a message written in ASCII characters, and I'm going to do some kind of weird mathematical operation on my set of characters so that I end up with something that looks like my cat just walked across my keyboard. The detail on that is whoever I'm sending this to has got to be able to reverse that operation. Because if the person I'm sending it to doesn't know how to get back to the plain text, I've just sent them gibberish. But I don't want anybody else to be able to take that ciphertext and turn it back into a plain text. So what do we do? Well, typically we use a password. So a password is an input to this algorithm that takes plain text and turns it into ciphertext in such a way that if you don't have this password, you can't go back to the plain text. So this is a really, really old idea. So one of the first examples of of a simple cipher is just a shift cipher. And the shift cipher, what do? You just add n to each letter. So let's say A is a 1, B is a 2, C is a 3, Y is a 25, Z is a 26. And maybe my password is 3. So what am I going to do? I'm going to take my message, I'm going to add 3 to each letter. So if my message is HELLO, H, that's the 8th letter. I'm going to change it into the 11th letter, which is a K. E is going to go from 5 to 8. L is going to go into an O, and O is going to go into an R. So what I would actually write on the piece of paper and have delivered to my friend is this. And if somebody intercepts this and reads the message, they don't see hello, they see this, and they have no idea what that means. If the message gets to my friend and I've previously told them the password is 3, what do? They take this and they subtract 3 from each letter, and they get HELLO, and they can read my original message. So this is encryption, and this is decryption. And there's a lot of different ciphers that we can use. You can do a transposition cipher. And a transposition cipher, you break your input into blocks. Let's say we're going to go into blocks of 4. And maybe we just add spaces at the end so that we have a multiple of 4. And we have a rearrangement algorithm. So my password might be the first character goes to position 3, the second character goes to position 1, the third character goes to 4, and the fourth character goes to 2. All right, so how do I encrypt this message? I take the T, I put that in the third position. I take the H, put that in the first position. Take the I, that's the third letter, put it in the fourth. Take the S, put that in the second. And then repeat that on the subsequent blocks. Take the first letter, put that in the third spot. So I'll do an underscore for a space. Put the second one first. Put the third one at the end. That's another, sorry, that's an S. And then put the fourth one in the second. That's another space. And so on. And so if somebody intercepts the message, they see this and they have no idea what it means. All right, so people have been using ciphers for thousands of years. Coming up with a good cipher is difficult. So what's the major weakness about a shift cipher, the way I've described it? Yeah, there's only 26 possible passwords. I mean, even if you don't have a computer, you can just start trying possible passwords until you start seeing words. So if you're motivated, an exhaustive search is pretty simple. So here's a different idea. instead of just adding a fixed offset, let's just take our letters and let's just map them to different destination letters. We'll just shuffle them all up, and I'll have a table saying, you know, A gets replaced by X, B gets replaced by W, C gets replaced by A, and so on. So how many different passwords are there now? Well, we'll find that out in about 4 weeks when we do combinations and permutations. But there's a lot of possible passwords, right? There's 26 things I can map this to. There's 25 things I can map this to. It's 26 factorial possible passwords. So, you know, again, with a computer, not a problem. But if I don't have a computer, it's pretty hard to just try all the possible passwords. But this is still a really weak cipher. And the reason it's really weak is because if you use this to encode something written in English, there's a really simple attack you can use. The attack is that if you look at English text, letters don't appear at the same frequency. The letter E is the most common letter, and it appears with a certain frequency that's greater than, you know, any other letter. So if my letter E was mapping to, I don't know, let's just say a J, what do? I take the encrypted text, the ciphertext, and I say which letter appears most. And chances are it's going to be the letter J. And that's going to tell me, okay, J is probably the letter E. And so I can take a frequency table for a lot of different letters and come up with an initial guess as to what this mapping is just based on frequency. Now, if you have one short message, this isn't going to work. But if somebody is pumping out page after page after page of ciphertext, the more ciphertext you have, the better this analysis is. And you can use combinations, right? For example, TH occurs much more often than KJ, right? So when I find certain combinations of letters appearing next to each other, I can start to speculate as to what those letters are. This is kind of like playing Wordle, if anybody plays Wordle on the New York Times site. Same kind of thing. You come up with these algorithms for making educated guesses. And that also works with things like transposition ciphers. Because if I'm always doing this arrangement, if TH occurs a lot in my text, I'm going to find lots of occurrences of an H followed by something followed by a T. And that's going to tell me, okay, those are probably next to each other. And you can work up from there. So good ciphers are difficult to come by. We are just about out of time, so I'm going to leave it there. Monday, we will extend this and talk about what makes a better cipher, and then talk about how we make it possible to do this on an internet where everybody has access to the actual packets that are being sent around. All right. That will be Monday. We'll finish up this unit and then we'll go back to talking about propositional logic and start working on mathematical induction. That's all I got. If you're in 222 tomorrow, I'll see you there. Otherwise, enjoy the rest of your week, and I will see you on Monday. All right, take care. Thanks.